My lecture today. Today, I think I'm proposing this to be the last lecture in the semester. Of course, on Monday, we're actually going to start revision. But if we're not able to finish this lecture slide, of course, we have to do the remaining or the remainder of that for maybe like 20 minutes on Monday before we go into revision. But let's see how we go. Okay, so once again, I want to welcome you to this topic. Let me remind everyone again, the final exam, we covered principal component analysis, repeated measure, and logistic regression, which means whatever we're doing now should be taken seriously. Okay, I want to welcome you to another exciting statistical topic. This is what we call the generalized linear model. Of course, the subtopic is a variance of logistic regression. We are still on logistic regression. Now, in the outline, I'm actually going to distinguish between generalized linear model and general linear model. They are not the same. Okay? Generalized linear model and general linear model, they are not the same. So I'm actually going to make a distinction between them today. Now, I'm also going to review, a case control study. Of course, the last lecture, we're not able to finish that. Then I'm, also going to talk about the case control study. Then finally, I'm going to talk about the variance of logistic regression. Okay, so let's get started. I need you to pay attention to this. Very, very crucial. What is the difference between a generalized linear model and a general linear model? I'm going to tell you that when the nature of the response variable is continuous, of course, we use linear regression. We use analysis of variance. Of course, the t-test and the like actually fall under what I call the general linear model. I'm going to say that again. When I say general linear model, what are the tests that am I referring to? I'm referring to linear regression. I'm referring to analysis of variance. I'm referring to t-test. I'm referring to, situation where the response is continuous. Okay, so we call that general linear model. I'm going to repeat that. Very, very crucial. I need you to take note of these. When I say general linear model, I'm actually referring to those tests that assume the response variable continuous. What are these tests? You remember your t-test. Assume a response variable to be continuous. Your analysis of variance tests, your linear regression, and so on like that. Let me also tell you something about general linear model. They all have these four assumptions that I'm going to mention. They all have these assumptions that I'm actually going to mention: linearity, constant variance, normality, okay, linearity, okay, constant variance, okay, normality, independence. What am I talking about? I'm talking about general linear model. I'm talking about assumptions of the general linear models. And that's why when you take a look at the analysis of variance we've been doing, the linear regression, we always talk about all these assumptions. Does that make sense to you now? That's what we call general linear model. But what do we mean by generalized linear model? There's a difference between generalized linear model and the general linear model. Now, I'm going to tell you the meaning of the generalized linear model now. The generalized linear model actually generalizes linear regression, okay, to allow the linear model to be related to the response, via what I call a link function. Via a link function, I'm going to say that again. The generalized linear model, okay, generalizes. Look at the word generalized. Generalized. So it generalizes linear regression, okay, now to allow the relationship between the linear model, okay, and the response, okay, and that very relationship is being captured by link function. And you know what link function does, right? I'm going to tell you what link function actually do. The link function transform the probabilities of the level of categorical variables. I'm going to write that now. What link function, I'm talking about generalized linear model, right? Okay, now I want to tell you, I said the generalized linear model, I say this generalizes linear regression, okay, allowing the the linear model, allowing the linear model to be related to response, okay, via link function. Let me see if I can get another marker. This is not taking good to manage. Oh, can you see what I'm writing on the board, right? Okay, now via link function, okay, now what is the function of a link function? The link function allow the magnitude, allows the magnitude, okay, of each measurement, okay, to be to depend on its predicted value. Now let me tell you what the link function does. The link function actually transform the probabilities of the levels of the categorical variable into a continuous scale. When you are working with if a situation where the response variable is it's not continuous, we can now use a general linear model anymore, okay, which means we need to use a generalized linear model. What the generalized linear model is going to do is going to transform the probability, okay, of the levels of that categorical response, okay, into a continuous scale, okay, and that very continuous scale will be unbounded, okay. It's going to be unbounded. I'm going to write that now. It's going to be unbounded, okay. So a link function transforms the probabilities of the levels of categorical response into a continuous scale, that is unbounded. Of course, the categorical is bounded. Remember the other time when we're dealing with the 0, 1, right? The reason why linear model cannot be used, because linear model cannot be used, the prediction is going to go over the range of 0 and 1, even though other assumptions can be fixed, but there's no way the whatever efforts you do cannot restrict the range into 0, 1. And that was why we go for other form of a model. Let me tell you this: logistic regression, okay, and other variants of logistic regression, they are classified under generalized linear model. So I'm going to say this again. The general linear model that you see, the general linear model is actually talking about situation where the response is continuous. Like general linear model. An example of such: linear regression, analysis of variance, t-test, and so on like that. And they all have assumptions of linearity, normality, constant variance, independence. But what if in a situation where the response variable is categorical, then we cannot use general linear model anymore. What do I mean by not using general linear model? It means I cannot use ANOVA, I cannot use linear regression, I cannot use t-test, I cannot use any method, okay, that assume linearity, normality, constant variance, okay, and independent. That's what it means. Does that make sense? Now, by generalized linear model, okay, that we enable the linear model now, it's going to generalize the linear regression and enable the linear model to be linearly related to the response. But how can that possible? That will be possible by link function. And what is the function of the link function? The link function will now do a job. Okay, I know you, response, you are categorical, you are bounded, but I'm going to do something to make sure you are unbounded. Because it is only when it is unbounded that you can now finally apply linear regression. Even in logistic regression, we apply linear regression, but a link function has already done its job. What is the function of, what is the job? What is the role of link function? The link function will transform, okay, the probability of the levels of the categorical response into a continuous scale. Because before you can apply linear regression, you need a transformation to a continuous scale. Any question? Exactly what we're doing now. Okay, so what I'm trying to say in essence that, the logistic regression that we've done, okay, and the variants of logistic that we're going to do, they are all captured under the generalized linear model. The fact remains, the nature of the response was not categorical. We needed a link function that transformed that into a continuous scale. But you know what? In the end, we still use linear regression. But the linear regression was possible after transformation to a continuous scale has already been achieved. Okay, I want to go back to review a case, the case control study. Of course, the other time when we're doing this, I told you, when we're talking about, if we want to establish relationship between a particular risk factor and maybe to a response, of course, we're going to go into population. We're going to choose those who actually have maybe a disease and those who do not have. And we're going to ask the two group questions, whether they were exposed or not. Okay. And of course, that was what we did the other time. And what we now want to do is testing, and this is going to, we call this odd ratio. Of course, in logistic regression, we talk about odd ratio. Now here we are still under the generalized linear model. Okay, so what is it? If I'm testing that the odd ratio equal to 1, it gives the odd ratio is not equal to 1. If odd ratio equal to 1, what are we trying to say? If odd ratio equal to 1, then we are trying to say the relationship between the risk factor and the response, that relationship is not significant in a way. That's what we mean. They are not related. And when the risk factor, the odd ratio is not equal to 1, then we're trying to say there's an association between them. Okay, I showed you this picture the other time. We go into the population, we choose, people that have the disease and those, and I'm calling that disease cases now. Okay, outcome is present in, we identify group in the population where the outcome is present. We identify another set of group where the outcome is not present, and of course the one where cases, the outcome is present, we're going to call that a treatment group or experimental group. The second one, we're going to call it a control. Okay, now we're actually going to partition those whose outcome is present into two, because from what they're going to tell us, we're going to ask them, oh, you have the disease. Okay, does that mean you are exposed? Are you exposed to something or not? We're going to see some of them that will say they are exposed or not. In the other group, we're also going to see that. Okay, now we're actually going to have a layout like this, which I call this a contingency table. Contingency table. This is what we call a cross tabulation. You know what? We know what is going on here. Oh my God, we got two variables here. They are categorical. Okay, the one variable is the one that have cases and control. The other variable is exposed and unexposed. We got two categorical variables here. Each has two levels. And you know what we're going to call this? Analysis of categorical variables. You know why? Because we're looking at the relationship between two variables that are categorical. They got two levels. In a situation where you want to analyze that, we're basically going to analyze the odd ratio. Now, I call that odds ratio. It means they're basically going to be two ratio. Well, we're going to be looking at a ratio of two ratio. What will be the first one? The odd of exposure among cases. And what will be the second one? The odd of exposure among control. Take a look at that. So the odd of exposure among cases is basically going to be A over C. And when I say odd, among cases, some will be exposed, some will not be exposed. The ratio of those who are exposed to those who are not exposed among cases, that's why you see A over C. We're also going to do the same to control. Okay, in the control group, how many of you are exposed and how many of you are unexposed? Okay, the B is the number that are exposed in the control group, and D is the number that are unexposed in the control group. What would be the odd? That would be B over D. And I'm not going to do the odds for that. Now, please take this very, very important. In statistical analysis, if you have done beautiful analysis and you don't interpret, it doesn't make sense. Interpretation is the key. Okay. Now, when odd ratio equal to 1, when odd ratio greater than 1, when odd ratio less than 1, those are the possibility that you can actually get. When odd ratio is equal to 1, you're going to have odd of the disease is the same for exposed and unexposed. If it's the same, you know what happened? There's no relationship between the risk factor and the outcome. That's what it means when odd ratio equal to 1. But when odd ratio is greater than 1 or less than 1, there is a relationship that we now need to identify. What kind of relationship? Okay, because you know why? Relationship could be negative, relationship could be positive. But in a situation where the odd ratio is greater than 1, we're going to say the exposure increases the odd of the disease. If it is less than 1, we're going to say exposure decreases the odd of the disease. I want to take a look at that. Now, we have an example here. For instance, a study that was conducted, in a confirmed case of cancer. Okay, it said conduct a case control study to determine if there's an association between colon cancer and diet. Association is the same thing as relationship. Does that make sense? Okay. Now, of course, you're basically going to look for two group of people in the population that have where outcome is present or not. Now, they got odd ratio to be equal to 4. Of course, you know the meaning. That's greater than 1, right? Odd ratio equal to 4 means greater than 1, right? Okay. Now we say individual who consume a high fat diet have 4 times the odd of colon cancer than individual who do not consume that. Please take note of that interpretation. Now, when the odd ratio is less than 1, is 0.6. Okay, we said the odd of colon cancer among coffee drinker is only 0.6 times the odd among the individual who do not consume. What I'm just trying to tell you here, just for you to be able to know how to interpret your odd ratio. Now, We have another example here where we have two groups, cases, those who have mumps and those who are heady. And of course, you actually want to look at the effects of, some get vaccine, okay, with booster, and some did not get. Let me tell you, what is the essence of getting vaccine? The essence of getting vaccine is probably to prevent an illness, or when somebody have illness, maybe not to get sick, something like that. Now, if you take a look at what I have now, okay, 251 actually have mumps, and you know what? They got vaccine. Okay, but 749 do not get vaccine, and they have the disease. Let me tell you this: my vaccine is not a magic. We don't, vaccine is an intervention. There's always going to be an error, right? You can see that even those who get vaccine and booster, we still have some who actually develop the disease. But except that, those who did not get vaccine, a good number of them get the disease. That's another way to show that the vaccine is working. But the fact that the vaccine is working does not mean vaccine is working perfectly, because there's always going to be a place of error. Now, take a look at what we have now. Just if you find the odd ratio, you see 251 divided by 749. We're trying, among cases, we're looking at the odd of the vaccine against not getting vaccine. That would be 251 divided by 49. We got that one for the cases. We also go to get the same for the control, those who are heady, right? And that will be 373 divided by 627. What is the odd ratios in general? We have a 0.5633. What is it meaning? A 0.5633 is classified under the odd ratio less than 1. Does that make sense? Now, we're going to say the odd of getting mumps. Why do I say mumps? The ops is in the numerator. Okay, the odd of getting mumps among students who got the vaccine booster is 0.56 times the odd of getting mumps among students who did not get the vaccine. This is to show you that the vaccine is working, because here what we have in the numerator is actually getting disease. But when the odd ratio is less than 1, that actually favor the one in the numerator. Does that make sense to you now? So which means the odd of getting the odd of getting mob among students who got vaccine is actually 0.56. That's okay, which means vaccine is working. Okay. Now, this is just to show you the formula, that we use in getting odd. Of course, we got 0.5633, right? So this is the formula. The odds in the numerator is more or less like pi into x plus 1 divided by 1 minus pi into x plus 1. While the one in the denominator is a regular one that you know about. It's going to be pi x divided by 1 minus pi x. And you know what? Don't forget, when you have the 0.5633 here that you actually have, okay, if you run a logistic regression model, that is the value we're going to get after exponentiating. I'm going to say that again. The odd ratio that we just compute now, you don't get this directly when you run a logistic regression. When you run a logistic regression, you're going to get log odd estimate. Now, what are you going to do to get an odd? You're going to exponentiate. You know what I mean, right? And that was why I said the exponentiation of negative 0.5739 will actually give us that. Okay, now, what am I trying to explain here? I need to look at the first model. That's a logit model, logistic regression in logit form. What do I mean by logit? Okay, and what do I mean by beta 1? If you take a look at the beta 1, it's just going to be the difference between the logit of pi 1 minus pi 0. Don't forget, where do I get 1? Where do I get 0? It's like moving when there's a unit increase in predator, probably from 0 to 1. So if you take a look at what I have now, okay, this is a mathematical expression that depicts what I've been explaining. Now, do you know something? If I go to the table, Take a look at this table now. I want to use the idea of logistic regression on this table. I'm confirming to you, logistic regression can be used in the analysis of categorical variables. Anytime you see data set in a table like this that is cross-tabulated, we actually call that analysis of categorical variables. The idea of logistic regression can be used. Do you know that what I got here the other time, using mathematics, that I got the odd ratio of 0.5633, I can actually code this guy here. How am I going to code this? I'm going to use the idea of logistic regression, which I'm going to show you now. Take a look at that. Moms, 251749, right? Where do I get 251749? Take a look at that. Do you see 251749 in cases, right? We're going to do the same to control. Now I'm coding that now. Okay. Now Eddie, 373,627. Vaccine. Vaccine is categorical. It's either you get it or you don't get it. If you take a look at what I have here, take a look at the table. Got vaccine, did not. You see that, right? I'm going to write that as yes, no. Then I'm going to model that. Look at the GLM. That is generalized linear model. Do you see that GLM? That's a generalized linear model. Now you're going to put moms, comma, Eddie. Okay, you see what I'm putting now? Please take note. Moms, Eddie. Okay, then I'm regressing that on the vaccine. Then I'm going to specify family equal to binomial. Let's see what we got. I needed to pay attention to the estimate negative is 0.57392. We call that log odd estimate. Do you know that if I take the exponentiation of that, I will find myself, I'm going to show you where I'm going to find myself now. When I exponentiate that, I'm actually going to find myself somewhere here that I'm going to show you now. You see that? When I exponentiate negative is 0.5739, that will give me 0.5633 that I computed manually the other time. You see that? Okay. So that is going to give you that automatically. So what I'm trying to tell you now is when you exponentiate negative is 0.57392, you're actually going to get the odd ratio. That's what I'm doing here using R. Can you confirm that? Can you see ESP? Okay, ESP, the coefficient now. Look at the vaccine. Yes, that is 0.5633141. The one I got the other time when I was going mathematical, when I was going manually. Can you see that now? Then I can find the confidence interval of the odd ratio. This is the confidence interval of the odd ratio. Take a look at that. Then I can also conduct a chi-square association. Let me tell you this. When two variables are continuous, if you are seeking to get a relationship, you use correlation. Does that make sense? But when two variables are categorical and you want to get a relationship for categorical variable, you don't use correlation, you use a chi-square. Can you see chi-square now? That's what we are talking about chi-square test of independent or association. Take a look at that. And I know for those of you who have done 3011, okay, who have done 3011, you've done something like that. Okay. Now, when you look at the relationship now, look at the p-value of the relationship. That is significant. When the p-value is less than 0.05, when you conduct a chi-square test between the two categorical variable, that's what we got. You know what I mean? There's an association between getting the vaccine and contacting moms. That's what it means. Any question? Any question? Okay, now take a look at this. When we're talking about, I want to go back to the generalized linear model now. When we're talking about general linear model, the response variable has an error distribution that is normal. I'm going to say that again. You know, I said there's going to be multiple choice, right? There are some things I'm saying today that may be part of the exam. And if you don't get what I'm saying, please ask me a question or you watch my video. I'm going to say that again. General linear model, okay? The response variable in general linear model is assume a normal error distribution, which means the distribution for the response is assumed to be normal. Does that make sense? That was why we normally investigate normality, okay? But what about the generalized linear model? Okay, the error distribution is non-normal. That allow variety of error distributions other than normal. I'm going to say that again. Generalized linear model, okay, allow variety, okay, of error distribution that is other than normal, that is not normal. But when we talk about general linear model, the error distribution of the response is assumed normal. But for generalized linear model, the error distribution for the response is other than normal. Does that make sense to everyone now? So which means when I'm talking about logistic, and that was why I take a look at the board. When we are running ANOVA, linear regression, they are classified under general linear model. The error distribution should be normal. That's why you see normal. And the link function is identity. We don't need a rigorous link function because the nature of the response is already in a continuous scale. We don't need any transformation. But what if in a situation where the distribution is binomial, then I'm no longer talking about general linear model. I'm talking about generalized linear model. Then the link function will not be identity anymore. The link function will be logit, because the logit will enable the probability of the levels of the categorical response variable to be transformed or translated or converted into a continuous scale. And that's what I'm showing on the board. Take a look at that. Now let me also tell you this. The method we use for general linear model is the ordinary least square. I'm going to say that again. The method that we use for general linear model is ordinary least square. But which method do we use for generalized linear model? We use the method of maximum likelihood. Please take notes. Go ahead. Okay, this is what I'm trying to say. For general linear model, the method, like when I say general linear model, I mean ANOVA, linear regression. We use ordinary least square method. Have you heard about ordinary least square? Okay, I'm going to write it down. Thank you so much. Okay, ordinary least square. That is what you call OLS. Does that make sense? That's what we use for general linear model. But for generalized, we use the method of maximum likelihood. Does that make sense to everyone? Okay. Okay, now, and take a look at what I'm saying. I said, point to consider. You should check for empty or small cell by doing a crosstab between the categorical variable predictor and the outcome variable. If a set has a few cases, the model may be unstable. What we're trying to say is that we need to have more cases. More cases here is more or less like go into the population, take large sample. Those who have the disease and those who do not have, don't just take small. Does that make sense? That's what it means. Otherwise, it will be unstable and you're going to mislead. Another point to note is sample size. Logit model require more cases than OLS. What I say logit, the logit is for the generalized, right? OLS is for the what? General linear model. Okay? And that is the reason why I say that. Okay. I want to go to a topic that I know, a subtopic that I know I may not be able to finish. But you know what I'm going to do? I'll first like tell you the meaning of this in 15 minutes. And everything that you're actually going to see that will follow that is going to be arrow code and results. I need you to pay attention now. I need everyone to pay attention now. I'm going to look at the story. When the response variable is continuous, and I basically want to study relationship, of course, you know, I'm going to use general linear model, which maybe I want to do ANOVA, linear regression, and so on like that. But what if in a situation where the response variable is categorical? I can no longer use a general linear model. Then I'm actually going to use a generalized linear model, where the link function will no longer be identity. The link function will be a logit. Now, I've walked you through the use of logistic regression in this class. And we call that binary logistic because the level of the response is categorical and we got two levels. That is binary logistic. Do you know we also have other form of logistic regression, which I want to discuss now? We have ordinal and we have multinomial. But before I start showing you the slide, I want you to understand the difference between binary logistic, ordinal logistic, and the multinomial logistic. Please pay attention now. For binary logistic, the response variable has two levels. That's for binary logistic. That's what we've been doing. But for ordinal logistic, we got more than two levels and they are ordered. I'm going to tell you the meaning of ordered. For instance, take a look at the example, size of automobile, subcompact, compact, mid-size, large. That is like ordered, right? Maybe from the smallest to the largest, right? That's an example. You know, what if in a situation where my response variable is categorical and the numbers of levels is more than two, but they are also ordered. When they are ordered, we're actually going to use ordinal logistic. What's another example? Political philosophy. Now, I want you to take note of this. Political philosophy is different from political parties. Do you know that? Okay, I want to use United States as a typical example now. Political parties, if I talk about Democrat, Republican, Independent, they are not ordered, but they got three levels. They are not ordered. Then if I want to feed logistic, that would be multinomial. Does that make sense? Multinomial. But if I want to talk about political philosophy is ordinal. Look at that. Liberal, moderate. You know, I want to be that maybe liberal is here, moderate is in the middle, and conservative is here. That's an ordered, and that will fall under the ordinal logistic regression. Does that make sense? Like, for instance, those of you into marketing, maybe you want to ask about the perception of the customers about your product, your service. I know there's going to be a question like, do you strongly agree, neutral, disagree, strongly disagree? Take a look at that on the scale. That's an ordered one. Any question on that? Now you understand the difference between binary logistic, two levels, just two levels, two possible outcomes. Ordinal logistic, more than two, but they are ordered. Multinomial, more than two, they are not ordered. Do you know race is an example of multinomial? Race. Okay? Now, do you understand the difference now? Then I'm going to show you some code. Now, take a look at this. Admission into graduate school. Okay? We've used this example before. But if you take a look at the response variable depends on the prestige of the graduate school admitted into. One is the highest prestige, two is the medium prestige, and three is the lowest prestige. continuous GRE GPA, categorical undergraduate school rank. But let me tell you something now. To produce the correct sign on the estimate, you know what we want to do? The graduate school rank. We need a graduate school rank. Okay, the original rank was 1, 2, 3. The original rank was the rank of your undergraduate school, where they put 1 to be the highest prestige. But when you want to talk about that of the graduate school rank, it is 3, 2, 1 instead of 1, 2, 3. So the 3 now, okay, is going to be a graduate institution with the highest prestige. That is the 3. 2 will be the one that followed that, and 1 will be the lowest prestige. We're talking about graduate school now. Take a look at this. We want to make an ordinary response from GRE and GPA, where we're going to say, oh, some quality schools from graduate schools, you know, that are highly competitive. They're going to say their GPA, they're going to say, okay, greater than 3.85, and GRE greater than 725. What do you see? You see 3, right? What is the meaning of that 3? Graduate school with the highest prestige, not undergraduate now. You know, take a look at the 3 here. What do we use 3 to represent? If you look at the recorded rank, we're not talking about the original rank. The original rank was a rank of the undergraduate. The recorded rank is a rank of the graduate school. Does that make sense? Now, take a look at this code now. Now, when you see GPA less than 3.13, GRE less than 550, what is the meaning of 1, 2? You are talking about the graduate school, you know, they have a lower rank. The highest rank for graduate school was 3. Do you see that? Now, take a look at the data set here. Now, we want to produce a contingency table from the situation now. X tab, look at the X tab, rank plus the grad dot rank. The first rank is a rank of the undergraduate school. The grad dot rank is the prestige of the graduate school. Okay, now if you cross tabulate, you know what we're seeing now. You see rank 1, 2, 3, 4. The rank of undergraduate school was from 1 to 4, but that of the graduate was from 1 to 3. For instance, do you know what that 6 represents? The 6 represents the number of students that was actually admitted into a graduate school with a rank of 1, okay, and that 6 is coming from an undergraduate school with a rank of 1. Does that make sense? There's a rank for undergraduate, there's a graduate rank. Now, we're actually going to use ordinal logistic regression for that. The ordinal logistic is also going to be a logit of the log, only that we're going to be logit of the log of the probability of y less or equal to j given x, and divided by 1 minus that. I'm going to quickly take you to the code now so that you're going to see. I need you to focus the board now on the ordinal. If you want to run ordinal logistic, you need to load a package called mass, M-A-S-S-N-R. Then, if you are working with the ordinal, please don't put GLM. It's going to be P-O-L-R. Can somebody see that P-O-L-R? P-O-L-R. That is for the ordinal logistic regression. Now, what do you see? Can somebody tell me what is acting as a response variable now? Graduate rank. Here we are looking at the effect of GRE, GPA, and the rank of your undergraduate on the quality of the graduate school. The quality of the graduate school. When I say the quality of the graduate school, we have 1, 2, 3. 3 is the highest. 3 is the graduate school that have the highest quality. Does that make sense to everyone now? Now, let's look at the coefficient. This coefficient, the result is going to come out in this form. Okay, and what you can see, you are not going to see p-value. Or in ordinal logistic regression, it doesn't come with p-value. I want you to take a look at what you see here. But what are we interested in? Then it is when you are now we can calculate the p-value through this. Look at what I said. P-values are not automatically generated. Therefore, they can be approximated by computing the probability of more extreme t-value using the normal distribution. Now, if you follow that, C table, COEF of the summary, don't forget initially you have a model here. In the end, they're actually going to have this. This will give you opportunity. Look at the effect of GRE, significant. Effect of GPA, significant. Take a look at that. Okay. Now, we are interested in the coefficients. Don't forget, these are log-odd estimates. Even in the ordinal logistic, we call them log-odd estimates. Now, do you know what I want to walk you through now? In the next 5 minutes, how do we interpret this guy? Let me tell you, there are two things we're going to interpret. Two things. Whether binary logistic, okay? Whether ordinal logistic or multinomial. Because of my time, I know we can't do multinomial today. We will do that for the next 10 minutes on Monday before we start revision. But I want to finish this. Two things will be interpreted. One, log-odd. Two, odd. Now, what do you see now? What am I getting? That is odd. What am I doing? I'm exponentiating. The value that I have here, if you take a look at 0.025, 6.81, they are all log odd. If I want to get odd, I'm actually going to exponentiate that. Then I do that to the fourth decimal. Let's do the interpretation for GRE. Like I said, there will be two interpretations for GRE. Number one for the log odd. Number two for the odd. Each of the variables, when you are interpreting them, you actually need the log odd and the odd. Now, let's take a look at the GRE from the table. The GRE from the table. Do you see the estimate? It's 0.025 something, right? Let's see the interpretation. I said, with 1 unit increase in GRE results in a 0.02 increase in the ordered, look at what I said, ordered log odd of the graduate school rank, given that all other variables in the model are head constants. You can see I mentioned ordered. Now, I've interpreted GRE on a log odd scale. What is the next interpretation? I'm still on GRE. I want to interpret that now on the odd scale, not on the log odd. And that's why I need this guy here, the exponentiation. What I'm going to be interpreting that will be 1.0260. Look at that. I said a 1 unit increase in GRE multiply the odd of getting into highest rank school. The highest rank graduate school I told you is rank 3. Okay. Now, if you want to be talking here, you're going to be, what is your numerator? Is the highest rank graduate school. What you have in the denominator will be the other two. The one and two. The 3 is the highest. The 1 and 2 are the lowest. Does that make sense now? So I said versus an average rank graduate school. I know the average rank graduate school will be 1 rank 2. Okay. And a low rank graduate school, the 1 rank 1. By 1.03, given that all other variables in the model are head constants. Why do I say all other variables in the model are head constant? Because it's not only GRE in the model. We also have to talk about them. We're going to do the same thing to every other one. I think I'm going to stop here today. I need questions. Yeah, go ahead. If I had a question correctly, you said for more than 3, do we still have 1 and the rest and the yes. The one we're going to put at the top is the one that have the highest rank. And that is our intention. We're always aiming at the top. We want to get to the top, right? That's what we're aiming at. That's a good question. Yeah. Any other question? Any other question? I'm going to see you on Monday. On Monday, we still have 10 more slide pages. We're going to go over that. That's going to be multinomial. But you can read that before Monday. But Monday is going to be our day of revision. before I start revision, I'm going to finish this. Then I'm now going to revise with you. Okay, another Friday. Make sure you stay safe and have a lovely day. Bye for now, everyone.